All right, welcome back, signature class. Now we're actually going to talk about aliens and life in the universe. But since we only have one example, which is life here on this earth, we've never found life anywhere else yet. We're still looking. Well, let's figure out how life formed here first, and then we'll start to look at places where we think life could form in the universe, the galaxy. So we have to understand exactly how life came to be on Earth first. And to do that, we have to go back to the formation of the solar system. How was the solar system formed? And we had alluded to this a little bit, but out in the galaxy, in the disk of the galaxy, there are these clouds called giant molecular clouds. And in these clouds of gases, dust, is where stars are formed. And these clouds of gas and dust circle in the disk of a galaxy, circle around the center of the Milky Way. Well, some 4.5 billion years ago, something triggered part of that cloud to start to collapse together. And once that started to collapse together, that cloud, all that gas will start falling in, and it'll fall in spinning into a disk. Same way that we would create a disk when the material fell into the black hole, you create a accretion disk. Same thing here, but it's not falling into a black hole, it's just coming into a clump. And once the clump gets bigger, it has more mass, it has more gravity. Once it has more gravity, it attracts more mass. And so you get this spinning disk of material. Most of the material ends up in the center, and that's where the sun forms. But in that spinning disk is where you form planets. These are nebulas that we see. By the way, this was the Eagle Nebula. And this is the Orion Nebula. Now, the Orion Nebula is probably the best and biggest, closest star-forming region to the Earth. And so this is where we learn a lot about how stars are formed. So if we look deep inside the Orion Nebula, we see these kind of stars right here. You see this. That is a solar system being created. That is the disk of material. That is also one behind it there too. This is one too. So this is the material that is collapsed together, spinning into the disk. We can actually see those disks being created or stars being formed right now in the Orion Nebula. That's what happened to the Earth 4.5 billion years ago. We know that's the case because the whole solar system is spinning counterclockwise. All the planets are revolving around the sun counterclockwise, and they're all revolving in the same plane of the ecliptic. They're all within a few degrees of the same orbit that the Earth makes around the sun. So they all formed out of this spinning disk, okay? That's why things like Pluto is not a planet anymore, because it was not formed that way. It was not in that disk. It was in the outer material beyond that, which isn't isolated to that disk of the ecliptic plane. Here's a close-up of that. You can see the disks here. Here's another disk up here. This is the disk too. These are new stars being formed in this cloud, this giant molecular cloud of gas and dust. Here's more of them. Every one of those is what we call a protoplanetary disk. Proto means before, so they're before they're planets. This is the disk out of which the planets will form. All right, then in that disk, this is an artist's conception, of course, all this material is spinning around. It spins around for millions and millions of years because it takes 30, 40 million years for the sun to form. It's going to take a long time. Well, all this material is spinning around, well, it starts to clump together. So the stuff runs into each other, and stuff that starts out as sand grain, then gets more sand grains, then becomes rock size, then becomes boulder size. Once it gets bigger, it gets more gravity, it starts to attract more until we build up planets. And then once you get bigger material, they start to run into them, so big chunks run into each other, they coalesce together, and you start building up planets. So in over millions of years, you get a few planets. The reason you only have a few planets is because eventually the planets are going to clear out all the other remaining stuff. And so once the stars starts to shine, its solar wind is going to blow out the remaining gas and dust, and the only thing that's going to be left are the chunks that are left over, which are the planets or any rocks, like things like the asteroids would be left over. Here's another artist's conception showing this disk of material, and then the planets would form in this disk. And that's why they're all spinning the same direction in the same plane. All right, so we're going to watch a video here. Hopefully this will load up. All right, so when the Earth formed, it was a molten sphere, as you can see here. And this is the moon. The moon was probably formed, and when a collision, the Earth ejected material out. But the moon was started out very close to the Earth. And the Earth would have been completely molten, completely liquid rock, which pulled it into a spherical shape. And there would have been massive amounts of volcanic activity. Yeah. Let's see if I can play that again here. Or this is a similar one here. So all this material comes together, collides, gets really hot. Well, then it would solidify, and the rocks would solidify on top of the Earth. And it would form these essentially continental plates like we have today. But they were floating on top of the liquid mantle underneath. It would be a very turbulent time in the Earth's history. So all these kind of collisions are going on because there's lots of rocks left over. And for the first about 100 million, several hundred million to a billion years, the solar system was a very crazy place for life to occur. All right, we're going to get into that now. So let's go back to the here. Okay, so there were lots of collisions and lots of turmoil in the Earth. But the key was, and we're not exactly sure the details, but we had to get water and we had to get an atmosphere. And we had to get a size that was sufficient so that we could hold our atmosphere and we were at the right temperature so we could have liquid water. So when we tried to look for life at other places, other planets we find out in the galaxy, we try to look for ones that are at the right distance and roughly the right size, because there's problems if it's too big or too small. If it's too small, it can't hold on to its atmosphere. If it's too big, the gravity might be so strong that it would cause other issues, like it'd be hard for animals to be on the surface if the gravity was so strong. And we see those kind of planets, very, very large planets close to their star. Okay. Then eventually, and we're not sure about this, but we filled up with water. Some people say the water was just leftover debris because we know water is a very common molecule in the universe. And there was water in that disk of spinning material. And so the water would coalesce together along with the rocks. But was that enough to fill up our oceans and make our planet 70% water on the surface? Maybe. Some people say maybe we also got a lot of our water from comets. Remember, comets are mostly water ice, and a lot of collisions going on. If comets were hitting the Earth, they would cause the impact, but all that water would stay there, eventually coalesce out, and that could have brought some of the water in to fill up the oceans. The atmosphere of the Earth was caused by all this material and what we call outgassing, which comes from volcanoes and stuff. When volcanoes erupt, not only do they erupt lava, but they also erupt a whole bunch of gases and stuff into the surrounding region. If our gravity is strong enough, it holds on to that. We believe when our solar system first formed, it created a very thick carbon dioxide atmosphere. At least 10 times, maybe even closer to 100 times thicker, higher pressure atmosphere than we have right now. But it was almost all carbon dioxide, no oxygen at all. Okay. Now, when did life form? It seems like, as far as we can tell, that life formed right after the Earth finally cooled, solidified enough so that there was a surface and liquid water. Once you had that, boom, life seemed to come right away, but the life started out as single-celled organisms. These single-celled organisms would then take carbon dioxide out of the atmosphere, release oxygen, photosynthesize, and reproduce. And that's all they did. But we see remnants of this carbon, which was left over by these single-celled organisms, 4.1 billion years old. Remember that the whole Earth is only 4.5 billion years old. So this life started very quickly right after. And the oldest things we see are these. They're called stromatolites. these little, they're rock structures. I think this is off the coast of Australia. But these rock structures were created by those single-cell organisms. When they would live, they would die, and when they would die, they'd leave behind these shells, and these shells would build up over time and create these rocks. And we can date these, and these date back to almost 4 billion years ago. So we know that life, single-celled organisms, formed very quickly on the Earth. And it seemed to form right away, which is why we suspect that on other planets, if you got the right conditions, it seems like, boom, life is just going to be there. Life finds a way. All right, now let's talk about our atmosphere. Our atmosphere now is 78% nitrogen, 21% oxygen. But originally, it was almost all carbon dioxide, 95% carbon dioxide, a lot of water vapor. Now our water vapor is like less than 1%. When we claim it's humid, it's still less than 1% of our atmosphere. But back then it would have been really thick atmosphere, tremendously thick. And the surface temperature, look, would have been super hot. So this would have been crazy. Humans like us couldn't live. But it took billions of years for this to occur. I mean, 2.5, 3 billion years. But all those single-celled organisms eventually turned our carbon dioxide atmosphere into an oxygen atmosphere. Where did the nitrogen come from? Well, nitrogen is kind of just a leftover product. And nitrogen, once you combine nitrogen with itself, you form an N2 molecule. It's a very stable molecule. And so that stable molecule is going to be around. So nitrogen just kind of, it hangs out in our atmosphere. Now it also gets used in the plant cycle, and nitrogen is used as a fertilizer too. But once you get in our atmosphere, it just kind of stays there. None of the animals actually use the nitrogen. It's just in our atmosphere.